In the previous lecture, we were discussing about the spanning set, bases, and dimensions of a vector space. Spanning set, basis set, and dimension of a vector space. Okay. Next. Spanning set, I explained you, spanning set is a set of vectors which can generate that vector space. Okay. I gave you examples of R2, R3, and some other spanning sets. But what is a basis set? Basis set is a set which can generate that vector space, as well as this set contains linearly independent vectors. Okay? That is a basis set. It has two properties. It should be a spanning set, as well as the set of the vectors in this set, they should be linearly independent. Then we call it a basis of a vector space. And what was the dimension of a vector space? Dimension of a vector space is the number of entries, number of vectors, number of elements in the basis set. Okay. For example, I gave you that example of if we have a set S1001. It's a set which is a subset of R2. Now this set is a spanning set because it can generate R2. And this set also contains the vectors which are linearly independent. So it is a basis set of R2. And what is the dimension of R2? Dimension is 2 here. It is basically, we can say that R2, these two vectors span R2, okay? And basis set is also, it is a basis set. It is basis set. Why it is basis set? Because the vectors in this set are linearly independent. So as it contains two vectors, so dimension of R2 is 2. Okay. Now, one very important thing which we need to know here is that any set, for example, I can say that 1, 0, 0, 1, and 2, 3. This set can span R2, but it is not a basis set. Why it is not basis set? Hamza? Anyone?
Sir, इसकी dimensions 2 नहीं है. ये linearly independent नहीं है.
Yes, that is the correct answer. These three vectors are not linearly independent because the third vector is a linear combination of the first two vectors. So it is a spanning set. We discussed this kind of set in the previous lecture. It can span R2, but the vectors in this set are not linearly independent. Okay. Here, the result is, the important result which I wanted to tell you is that this set can be reduced by eliminating appropriate vector और vectors में भी अगर उसमें 4 vectors हों या कोई और set है जिसमें ज़्यादा vectors हैं जो कि span कर रहा है किसी vector space को, तो उसमें हम कुछ vectors को eliminate कर सकते हैं, and we can reduce this set into some other set X as dash, which contains only those vectors which spans that vector space, as well as the vectors in that set are linearly independent. Okay, so any vector, any set which spans a vector space, a particular vector space, but it doesn't contain linearly independent vectors, then we can carefully eliminate those vectors which are not linearly independent, and we can reduce this set into a set which contains only linearly independent set, as well as this set generates that vector space. This is possible. Okay, and similarly, if we have a set which contains only one vector, for example, this one, इसमें आप क्यूब एग्जांपल ले लें. let we have a set S1, 0, 0 and 0, 1, 0. Okay, this is a subset of R2. Okay. Now this set, this is the reverse of that result. Now this set contains linearly independent vectors. It satisfies the second property of basis set. But this set does not span R cubed. Okay. We can extend this set. We can extend this set by incorporating or by adding appropriate vectors to make it a basis set. Now, it depends what kind of vectors you are looking for. For example, in this set, it is very easy to write a third vector, which is linearly independent of these two vectors, and the set of then those three vectors spans R cubed. It is very easy for R cubed, but for other general vector spaces, it is a bit technical. You have to go into more details of this thing. But remember these two results. If you have any question, you can ask me. There's a question in the chat window, maybe let me see it. Dependent. Sara Tariq. Can you talk to me if you have any question? Now we are going to discuss null spaces, column spaces, and row spaces. These things are basically related to matrices and linear systems. Now we are going back towards the linear systems and the coefficient matrix of the linear system. All these things which we have discussed about vector spaces, subspaces, linear independence, spanning, and many other things, all these things basically they help us in analyzing, in basically studying the solutions of linear systems. At the start of this course, I told you that we will be discussing only the system of linear equations and their solutions. So vector spaces, subspaces, and these kind of concepts, they basically help us to analyze solutions of the linear systems. Okay. Now, what we have discussed, we are going to connect all these things with the system of linear equations and their solutions. Okay. Hamza, you asked me a question before starting the lecture. How can we apply these things? Now, we'll see how we can apply these things and how can we analyze solutions of the linear systems. Okay. Okay, null space. Null space of a matrix. Because a linear system can be written as Ax equal to B, and this is the coefficient matrix. Okay, coefficient matrix, as well as the augmented matrix corresponding to this linear system AB. Augmented matrix is also a matrix, so that's why we are going to discuss null space of a matrix, row space of a matrix, row space of a matrix, and lastly a column space of a matrix. So first we shall discuss what is a null space, and it is basically corresponds to the solutions of homogeneous linear system. Okay? Homogeneous linear systems can be written in this form, and what we have in this, which is most important, is the matrix A, nothing else. Okay? You, Hanzala, what is the important thing in homogeneous linear system?
Sir, what was the question?
What is the important thing in homogeneous linear system? This matrix. Nothing else.
Yes, sir.
और कोई चीज है इसमें इंटरेस्टिंग? x तो अननोन है, वो तो हमने फाइंड करना है, सामने 0 है. तो if we can extract some information about the homogeneous linear system, we can only get that information from this coefficient. Yes? So what is a null space of a matrix? A null space of a matrix is nothing but a space which contains all possible solutions of a homogeneous linear system. Okay? So null space is what? It is a set. Null space is a set of all solutions of the corresponding homogeneous linear system. That is, if we have any matrix A, then null space is what? Null space is the set of all solutions of the corresponding homogeneous linear system. If we put that A in this form, Ax is equal to 0, where x is some unknown vector. So solution set of this homogeneous linear system is what? It's a null space. So if we look at this in the context of linear transformation, what do we get here? What is the null space? A null space is a transformation from R to R, I don't know, it is from N to M, defined by T of x is equal to Ax, such that T of x is equal to 0 for all x belongs to R, for all not x, for x belongs to R, Rn. In the context of linear transformation, what do we mean by a null space of a matrix? In the context of linear transformation, we say that if T is a linear transformation and it is defined by this, then the set of all possible x for which T of x is equal to 0 means all possible x in our N whose image is a null vector, whose image is a 0 vector. That set is what? It is a null space. So x, null space is what? Null space of A is what? It has x from Rn such that A times x is equal to 0. So this is how we define null space of a matrix. Okay. Now, how do we know this order of these R's, Rn and Rm? Now it depends what is the order of this matrix. If I say that its order is m cross n, then what should be the order of x? Anyone? In order to say that this multiplication is compatible, what should be the order of x?
Sir, n cross 1?
Yes, n cross 1. So in that homogeneous linear system, Ax is equal to 0. The order of n should be m cross n, and order of x should be n cross 1. So that these two things are equal and this multiplication is possible in terms of matrix multiplication. So what we obtain here, if after multiplying this, what do we get? What kind of vector we get? What would be the order of that vector?
Sir, m cross 1.
N cross 1. So this x should belongs to our n, and what we should obtain a vector in Rm. Okay, this is how we can fix the dimension of these spaces in the context of linear transformations. And we say that null space is the space containing all kind of vectors in where does this vector belong to? It belongs to
Rn.
Yes, of course, Rn. So that's why I have written here Rn. So you have to take care of these dimensions while solving these homogeneous linear systems. I hope you get it. What is a null space? If you have any confusion, if you have any question, you can ask me. Only about what is a null space and what kind of elements it contains. If you got it, let me move on then. How to find it? How to find a null space of a matrix? We must have two cases in this, in finding null space of a matrix. So let's discuss this with the help of example. नहीं, पहले cases discuss करते हैं. There are two cases. What is the case one? Case one. If the coefficient matrix A is square matrix. अगर आपके पास coefficient matrix जो है वो square matrix है plus A is non-singular. Okay. First thing is A square है और non-singular. What do we obtain? अगर A non-singular है तो Ax is equal to 0 का solution set क्या होगा? Null space क्या होगी इसकी? It's very easy. Anyone can tell me? What will be the null space of this thing if the coefficient matrix is invertible? In fact, there are two cases. The first is if the coefficient matrix is non-singular. The other case is the coefficient matrix is singular. These are two generic cases. The first case is the coefficient matrix is non-singular. If it is non-singular, obviously it will be a square matrix. Now, if A is non-singular, then what will be all possible solutions of this homogeneous linear system? Anyone?
So, trivial solution?
Yes, only one solution, which is a zero solution. Because A is invertible, we can take that thing on the other side, x equal to A inverse times 0, which is always 0. Okay. In this case, we have only one vector in this null space, and it is a vector space itself, so it will be a subspace of R and okay, that is the first case. Now the second case is, if you have any confusion in this, you can ask me. If there is no confusion, let me discuss the second case when the coefficient matrix is singular. When A is singular. Whether it is square or not, we don't care about that. But we only know that A is singular. In that case, A times X will have infinite many solutions. Infinite many solutions. Okay? It means in that case, null space of A, it will contain X belonging to R n such that X is what? We have to calculate the form of X here. And what would be the form of X? Let me explain this thing to you. It depends on a linear system. Okay? The form of an X will depend on the form of a linear system, or particularly a linear system. Let us discuss with this thing with the help of an example. For example, if we have a matrix A, this one, -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, 4. This thing. And we need to compute the null space of this matrix. This is equivalent to saying that if we have this linear system, for example, this linear system bx1 plus 6x2 minus x3 plus x4 negative 7x 5 equal to 0. First equation and second and third. If we have this kind of linear system, what would be the null space of this linear system, homogeneous linear system? Okay. So either in exercises, you can be asked to find the null space of homogeneous linear system or the null space of this matrix. In fact, this is the coefficient matrix of some homogeneous linear system. So in order to find the null space of this thing, what we do, we solve that homogeneous linear system. Okay, solve this thing. How do we solve it? I hope you know. If we write the corresponding augmented matrix which contains A as well as 0 vector. So you write the entries of A here, and the right hand side vector would be 0. And try to reduce it into echelon or reduced echelon form, whatever you like, reduced echelon form. And write back that homogeneous linear system. And then by introducing free variables, you can write the solution. I hope you can do it. If you have any confusion, you can ask me how to solve this homogeneous linear system. You can do it very easily. I hope you can. Now, after solving it and introducing appropriate free variables, how can we write the solution of this system? We can write the solution of this linear system in this way, x equal to some r 2 1 0 0 0 s 1 0 negative 2 1 0 plus t negative 3 0 2 0 1. So this is the solution of the homogeneous linear system corresponding to this matrix. Now, if I call this vector to be some vector u1 plus s u2 plus t u3. Okay, so x can be written in this form, where r s t are some parameters belonging to r. Now, what will be the form of x? You know it now. The form of x will be this thing. Okay? Or this thing. You can write it over there. Null space of this particular matrix, it contains x belongs to Rn, such that x is r times u1 plus s times u2 plus t times u3. Where u1, u2, u3 are this vector, this one, this one, this one. Now, you can see that all x belonging to null space are what? X is what? X is the linear combination of u1, u2, and u3. What does it mean? The span, null of A is the span of what? u1, u2, u3. Okay? So these three vectors are generating null space of A. Spanning. I hope you get it. You, Hamza?
Yes, sir.
Can you see the application of that thing now? So the spanning is basically, they are trying to help us in writing solutions of a linear system in a very compact form. Now, if someone asked me, what is the null space of this? I would say him, these three vectors can generate any solution to this homogeneous linear system. Okay? Now, what I understand that if I have these three vectors, I can write any kind of solution to this coefficient matrix or this homogeneous linear system. Now, I can choose the values of r, s, and t according to my requirement, and I can write the solution to this homogeneous linear system. Because there are infinite many solutions. in some practical application, what I require, I would definitely require only one particular solution which suits my application. So I can write that solution with the help of these three vectors, which are generating all the null space of that homogeneous linear system. Now, this set is spanning null space of A. Can I say that this set is a basis of null space of A? When can I say it? Anyone?
Sir, linear independence prove करनी पड़ेगी.
Still, we haven't checked whether this set is, the vectors in this set are linearly independent. So if I can verify whether these three vectors are linearly independent, then I say that this set is a basis for null space. Okay? Basis of null space of A. So I leave this thing as an exercise for you guys. Okay, try to check whether the set U1, U2, U3 is linearly independent. Okay, you have to verify it yourself. This set is linearly independent. Okay, just you have to check whether it is linearly independent. कैसे check करेंगे? क्योंकि अगर हम इन तीन वेक्टर्स को एक मैट्रिक्स फॉर्म में मैट्रिक्स के कॉलम्स में रखें और उस मैट्रिक्स का हम डिटर्मिनेंट फाइंड करें, अगर डिटर्मिनेंट नॉन जीरो है तो हम कहेंगे कि लिनियरली इंडिपेंडेंट है. अदरवाइज यू हैव टू वर्क मोर फॉर in order to know whether these sets are linearly independent. I hope you can do it. So if the set is linearly independent, then I can say that basis of null space of A is what? It is U1, U2, U3. अगर ये basis है null space की, तो null space की dimension क्या होगी? Dimension of null space of A is what? It is 3 because there are 3 elements in the null space, basis of null space of A. Yes, बोले.
Sir, ये स्क्वायर मैट्रिक्स तो नहीं है, तो इसका हम डिटरमिनेंट फाइंड नहीं कर सकते.
ये वाला नहीं है, लेकिन ये वाला तो होगा. इसमें 3 वेक्टर्स होंगे 3 डायमेंशन.
सर लेकिन वेक्टर्स को जब हम अरेंज करेंगे तो हमारे पास मैट्रिक्स कौन सा आएगा ऑर्डर का? कॉलम वेक्टर में लिखेंगे ना आपके पास यहाँ पे. सॉरी. लेकिन 3 कॉलम्स हैं. These are 5 dimensional vectors. I thought these are 3 dimensional vectors. So if it is not a square matrix, then how do you check whether they are linearly independent or not? I hope you all already know this thing. You write an expression of this kind, C1 U1 plus C2 U2 plus C3 U3 equal, you put it equal to 0, and then what you do, you try to prove whether after solving this homogeneous linear system, this is a homogeneous linear system again, after solving it, you try to prove that all the values of these parameters are 0. If all these C1, C2, C3 are 0, then these 3 vectors are linearly independent. If at least one of these C's is not equal to 0, then we say that they are not linearly independent. They are linearly dependent. Okay? Then in that case, in order to find the basis of null space, what we do? We use that result which I told you in the start of the lecture. We try to carefully remove that vector which is dependent on the other vectors. Okay, in order to get a subset of this vector which is linearly independent, as well as that set spans null space. That would be the basis of null space. And how can we remove that vector which depends on the other vector? It depends on the values of C. If you get the non-zero value of C, if you obtain any one non-zero value of C, then the coefficient of this parameter would be dependent vector. You can have these details in the book as well as, I hope I have already told you these things.
while discussing linearly independent and dependent vectors. So if you have any other question, you can ask me. This is how we find the null space, its spanning set, its basis set, and its dimension. Any questions? The next thing which we are going to discuss is the row and column spaces. Row, column space of a matrix. And this will help us in discussing linear systems. How do I write a general non-homogeneous linear system in this way? Okay? Okay? And that is the coefficient matrix. Remember this. If I say that, for example, this is the matrix in this homogeneous linear system, then what would be the order of A? Order of A, order of X equal to order of B. What should be the order of X and B if we have this matrix? Anyone? What should be the order of? What is the order of this matrix? It is 3 cross
5.
5. So what should be the order of X?
5 cross 1.
5 cross 1. What should be the order of B?
3 cross 1.
3 cross 1. Yes. Now, if we try to connect these things with the linear transformations, what kind of linear transformation we can write here? T from R to R. What would be the dimension of first R?
So 5.
5. And second?
3.
3. Yes. And how do we define this linear transformation? T of X is equal to A times X, which is equal to B. Okay? This is how we define this non-homogeneous linear system in the context of linear transformations. Okay? Now, if we write only the rows of this matrix, what would be the rows? R1 would be what? It would be -3, 6, -1, 1, 7, -7. And row 2 would be what? Row 2 would be 1, -2, 2, 3, -1. And row 3 would be the third row of this matrix, this one. And if I try to write the columns of this matrix, what would be the column of this matrix? How many columns are there? 1, 2, 3, 4, 5. So C1 will be what? -1, -3, -2, 1, 2. C2 is 6, -2, 4. C3 is -1, 2, 5. C4 is 1, 3, 8. And C5 is -1, -7, -1, -4. So now we have these 3 vectors, row vectors. If we take all the linear combination of these 3 row vectors, we'll get a space. We get infinite many vectors. Okay? Set of all linear combinations of these 3 row vectors means what is the linear combination of these 3 row vectors? It is what? Some alpha 1 R1 plus alpha 2 R2 plus alpha 3 R3. Okay? So by varying alpha 1, alpha 2, alpha 3, which belongs to R, alpha 1, alpha 2, alpha 3, they belongs to R. By choosing different values of alpha 1, alpha 2, alpha 3 individually as well as simultaneously, okay, we can, how many vectors we can obtain? Infinite many. But those infinite many vectors forms a space which is called a row space. And that space is a subset of what space? Anyone? Can you tell me? Hamza.
Yes,
Row
sir.
space. Row space में क्या होगा? Row space of A is what? It contains X belongs to, I'm not going to tell you, such that X is a linear combination. X is a linear combination of R1, R2, and R3. Okay, this is the row space. Now, tell me what space this X belongs to and what space this row space of A is a subspace. These two questions. Can anyone tell me?
R5.
X belongs to what?
R5.
R5. And what is this space, the subspace of? Subspace of R5 obviously. जिसको ये एलिमेंट्स बिलोंग करेंगे उसी की तो रो स्पेस सबस्पेस होगी ना. जिस स्पेस के एलिमेंट्स होंगे इस स्पेस में R5 ये स्पेस ठीक है. इसमें कितने एलिमेंट्स हैं R5 के? इनफिनिट मेनी. R5 के एलिमेंट्स हैं तो ये सब स्पेस जो होगी ये फिर R5 की ही सब स्पेस होगी. Whereas we have 3 row vectors, but each vector belongs to what? This row vector belongs to what? This row vector belongs to R5 because it has 5 components. So each vector belongs to R5, but we have only 3 vectors. So the space where this row space of A belongs to, it depends on the dimension of the vectors, not the number of vectors. So remember this. I hope you get it now. Now, you tell me now, the column space of A is what? Column space of A is basically the space which is generated by or spanned by columns of a matrix. So how many columns are there? 5 columns. The set of all linear combinations of these 5 columns, column vectors, will form a column space of that matrix A. And each individual column belongs to what? It belongs to
R3.
It has 3 components, so it belongs to R3. So the column space contains the elements of R cube. So the column space must be a subspace of R cube. Okay? So यहाँ पे अगर आप column space define करें एक ही, पहली चीज क्या होगी? इसमें जो elements हैं X वो belong करेंगे R3 को. Such that X is a linear combination of column 1, column 2, so on, column 5. And this column space is a subspace of R3 because it contains the elements of R3. Because each column has 3 components, so it must belong to R3. I hope you get it. The dimensions and vectors and spaces and what are they subspaces of. I hope you get it. If you have any confusion, you can ask me. If you have any confusion, you can ask me. Otherwise, I'm going to erase it. I give you a few seconds to think over it. Then you can ask me. Now, we know that how to find the null space of a matrix. Now, we are going to discuss how to find row space and column space of a matrix. For example, we choose this matrix. How to find its row space? Before discussing this, how to find row space of A, in column space of A, we need to discuss a couple of results or theorems before doing this. Those theorems are very important, and they help us in finding column space and row space of a matrix. If you have any question, meanwhile, you can think about it and ask me if you have any question. Those results are, let me discuss with you. The first result are theorems. You can say that. You can read these theorems and the proofs from the book, but I'm going to only discuss the statements of this theory. The first thing is, the first theorem is elementary row operations do not change null space of a matrix. Okay? Elementary row operations. This result was basically for the null space of matrix. Elementary row operations do not change null space of a matrix. Means आप किसी भी मैट्रिक्स पे एलिमेंट्री रो ऑपरेशंस लगा दें. क्यों? क्योंकि उसकी नल स्पेस क्या होती है? It's basically the null space of a matrix is this basically the set of all solutions of the corresponding homogeneous linear system. और homogeneous linear system में जब हम augmented matrix लिखते हैं तो हमने पहले भी equivalent matrices या equivalent linear systems का concept discuss किया हुआ. What is the equivalent linear system? Equivalent linear system, if we apply those three elementary row operations on any linear system, the resulting linear system which we obtain is equivalent to the original linear system. We discussed this result, this thing before while discussing elementary row operations. Okay. Elementary row operations do not change the null space. Similarly, elementary row operations do not change the row space of a matrix. Okay. They also null space as well as, or you can say that row space. Elementary row operations do not change the row space of a matrix. Because why? Because row space, we discuss it in the context of non-homogeneous linear systems. And when we write augmented matrix, okay, augmented matrix, in that augmented matrix, if we choose the rows, if we multiply or if we apply any elementary row operation on the rows of augmented matrix, it doesn't change anything. But for the column space, the elementary row operation will change. Why? Because in a non-homogeneous linear system, the columns are different. We cannot apply elementary row operations on columns. They will definitely change the structure and the solutions of the linear systems. Okay. So, elementary row operations do not change the null space or row space of a matrix. This is a very important result. The next result is, I'm going to read it only. You can see it in my notes, which I have uploaded in lecture 21, page number 4. If A and B are two equivalent matrices, now we are going to talk about those equivalent matrices. अगर आपके पास दो equivalent matrices हैं, A और B, the second side. अगर आपके पास A और B दो matrices हैं, and they are equivalent, what does it mean? We can obtain B by applying any number of elementary row operations on A. After applying elementary row operations on A, we can get B. And then we can say that B is equivalent to A. Okay? For example, if we try to reduce A into reduced echelon form and the resulting matrix, which is in the reduced echelon form, we call that matrix B, which is the reduced echelon form of the matrix A. Then they are basically equivalent matrices. Okay? So if A and B are two equivalent matrices, where B is obtained by applying series of elementary row operations of A, and B is in reduced echelon form. Then we can say that column vectors of A and column vectors of B, or you can simply say it, column vectors of A are linearly independent if and only if column vectors of B are linearly independent. Okay? Means column vectors of A are linearly independent if and only if column vectors of B are linearly independent. Now, in order to find the column space and its basis फाइंड करने के लिए क्या कंडीशन है? दो कंडीशंस. बेसिस के लिए आप तो एक तो उस स्पेस का स्पैनिंग सेट चाहिए होता है, एंड दैट स्पैनिंग सेट वी ऑलरेडी हैव इट. रो स्पेस का स्पैनिंग सेट क्या होगा? अगर हम यहां पे कॉलम स्पेस फॉर एग्जांपल लिखते हैं, कॉलम स्पेस ऑफ ए, इसका स्पैनिंग सेट क्या होगा? एनीवन?
Sir, sum of all of the columns sum of all of the columns in the matrix.
Not sum. So columns of that matrix. How many columns are there? C1, C2, C3, C4, C5. हमने पहले क्या कहा था स्टार्ट में? Column space क्या है? Column space is a space which is generated by columns of a matrix. So the spanning set column space का क्या होगा? इसके columns होंगे ना, जितने भी कॉलम्स हैं इस मैट्रिक्स में, तो वो उसका स्पैनिंग सेट. जी जी
सर, ये आर क्यूब को बिलोंग करता है. टेक्निकली आर क्यूब का जो बेसिस सेट है वो भी इसका स्पैनिंग सेट नहीं होगा?
ये स्पैनिंग सेट है कॉलम स्पेस ऑफ ए का, और कॉलम स्पेस ऑफ ए सब किसकी सबसेट है? R3 की. तो R3 को जरूरी नहीं है 3 वेक्टर्स स्पैन करें, 4 वेक्टर्स भी कर सकते हैं R3 को स्पैन, 10 वेक्टर भी कर सकते हैं R3 को स्पैन कर सकते हैं या नहीं?
यस सर. सर तो जो इसका स्पेस बनेगी तो नेसेसरी नहीं है कि इसका जो स्पैनिंग सेट हो वो इसके अलावा भी अगर कुछ जनरेट कर सकता हो तो फिर भी वो स्पैनिंग सेट होगा.
वी आर स्टार्टिंग विद दिस माय डियर. हम कह रहे हैं कि ये कॉलम्स जो हैं कॉलम स्पेस को जनरेट करें. सबसे पहले स्टार्ट में, इस लेक्चर के स्टार्ट में मैंने क्या कहा था कि अगर आपके पास एक स्पैनिंग सेट है जो कि स्पैन कर रहा है किसी भी कॉलम स्पेस को, किसी भी स्पेस को, हम इसको रिड्यूस कर सकते हैं या नहीं? बाय एलिमिनेटिंग सम कॉलम, सम वेक्टर्स व्हिच आर डिपेंडेंट ऑन अदर वेक्टर्स. वी कैन रिड्यूस दिस सेट. कैन वी?
यस सर.
ठीक है. अभी हमने कहा कि ये कॉलम्स जो है वो इसको स्पैन कर रहे हैं. ठीक है, स्पैनिंग सेट हमारे पास आ गया. व्हाट वी आर ट्राइंग टू फाइंड हियर, we are trying to find the basis of a column space and the dimension of a column space, as we did for the null space of a matrix. Okay? So अब हमें ये पता है कि ये स्पैनिंग सेट है. अब हम ये चेक करना चाह रहे हैं कि ये जो वेक्टर्स हैं ये लीनियरली इंडिपेंडेंट हैं या नहीं. Okay? अगर ये वेक्टर्स लीनियरली इंडिपेंडेंट हैं तो ये इसका बेसिस सेट होगा कॉलम स्पेस का. एग्रीड?
Yes.
अच्छा, इसको लीनियर इंडिपेंडेंट चेक करने का अगर आपके पास कोई आसान मेथड आ जाता है. आसान मेथड क्या है? देखिए, इसको अगर आप लिखते हैं ना एज ए लीनियर कॉम्बिनेशन एंड पुट इट इनटू होमोजेनस लीनियर सिस्टम, मीन्स इसको हम क्या कहेंगे, अल्फा 1 C1 प्लस अल्फा 2 C2 प्लस अल्फा 3 C3 प्लस अल्फा 4 C4 प्लस अल्फा 5 C5. We put it equal to 0 and check whether all these coefficients alpha 1, alpha 2, alpha 5, they are 0 or not, in order to check whether they are linear independent or not. Because this is a very big homogeneous linear system, we have to put a lot of effort in order to solve it. What we are trying to do here, we are trying to minimize our effort to prove in a very easy way or efficient way कि ये कॉलम्स वेक्टर्स जो लीनियर इंडिपेंडेंट हो गए. हमने क्या कहा कि बजाय इसके कि इनको चेक करें आप कि ये लीनियरली इंडिपेंडेंट है या नहीं, हम क्या कर रहे हैं, हम इस जो मैट्रिक्स ए है हम इसको रिड्यूस एचेलॉन फॉर्म में कन्वर्ट कर रहे हैं. We are getting an equivalent matrix which is in the reduced echelon form. Now it is very easy to check in a reduced echelon form whether the row vectors or column vectors are linearly independent or not. It is very easy. Okay? So we were talking about the row space. अब हम row space किससे generate हो रही है? वो इसकी rows से. हम क्या कर रहे हैं कि हमने उसको चेक करना है, और जो रो स्पेस को जनरेट कर रहा है, स्पेन कर रहा है, वो तीन वेक्टर्स हैं, रो वेक्टर्स. अब हमने चेक करना है कि वो तीनों रो वेक्टर्स लीनियरली इंडिपेंडेंट हैं या नहीं. मींस बेसिस बना रहे हैं रो स्पेस की या नहीं. अगर बेसिस बना रहे हैं तो हमें डायमेंशन पता चल जाएगी. ठीक है, तो ये चीजें इसलिए हम कर रहे हैं. वी आर गोइंग टू डिस्कस दीस थ्योरम्स. बजाय इसके कि इन ओरिजिनल वेक्टर्स को हम चेक करें, हम क्या कर रहे हैं, इस मैट्रिक्स को मींस उसकी रोज और कॉलम्स को हम रिड्यूस एचेलॉन फॉर्म में लेके आ रहे हैं. रिड्यूस एचेलॉन फॉर्म में अगर आ जाता है तो हमारा काम बहुत आसान हो जाएगा लीनियर इंडिपेंडेंट चेक करने का. हमें सिर्फ स्पेनिंग की फिक्र होगी, लीनियर इंडिपेंडेंट की फिक्र नहीं. ठीक है, आई होप यू गेट इट. इफ यू हैव एनी क्वेश्चन यू कैन आस्क. नो क्वेश्चन? ओके. अभी हमने ये कहा कि एलिमेंट्री रो ऑपरेशंस जो है वो नल स्पेस और रो स्पेस को चेंज नहीं करते. मींस जो ओरिजिनल वेक्टर्स जिस रो स्पेस को स्पेन कर रहे हैं, जो उसके इक्विवेलेंट मैट्रिसेस में वही वेक्टर्स होंगे जिस उसी स्पेस को जनरेट करें, उसी कॉलम्स पे, उसी नल स्पेस को और उसी रो स्पेस. ठीक है, आई होप यू गेट इट. मसलन अगर हमारे पास ये मैट्रिक्स है, हमने इसको कन्वर्ट कर लिया रिड्यूस्ड एचेलॉन फॉर्म. इसकी रिड्यूस्ड एचेलॉन फॉर्म क्या होगी? आई रोट इट बिफोर, मे बी समवेयर. लिखी थी मैंने ये पहले. While solving the homogeneous linear system. हाँ, ये इसकी जो एचेलॉन फॉर्म, सॉरी रिड्यूस्ड एचेलॉन फॉर्म है, रिड्यूस्ड एचेलॉन फॉर्म या आप सिर्फ एचेलॉन फॉर्म लिख लें, दैट इज आल्सो सफिशिएंट. ठीक है, आई डोंट नो इसमें क्या लिखा हुआ है एचेलॉन फॉर्म. इसने रिड्यूस्ड एचेलॉन फॉर्म लिखी है. दैट इज 1 -2 0 -1 3 0 0 1 2 -2 0 and 0 0 0 0. अच्छा, रिड्यूस्ड एचेलॉन फॉर्म हमें क्या बताती है? जो लीनियरली डिपेंडेंट वेक्टर्स होते हैं ना, वो जीरो हो जाता है. मतलब आपकी ये रिड्यूस्ड एचेलॉन फॉर्म है बी ए की. अब आपके पास यहाँ पे तीन रो वेक्टर्स हैं. आपको नहीं पता कि कौन से लीनियर इंडिपेंडेंट है, कौन से डिपेंड कर. यू नो ओनली दीज थ्री वेक्टर्स. जब आप रिड्यूस्ड एचेलॉन फॉर्म में इसको कन्वर्ट करते हैं तो जो नॉन जीरो रोज होती हैं वेक्टर्स की, वो हमेशा लीनियर इंडिपेंडेंट होगी, और जो जीरो रो हो जाएगी वो वेक्टर ऑब्वियसली इन दोनों वेक्टर्स के ऊपर डिपेंड कर रहा हो, तभी तो वो जीरो हुआ है. सो इट मींस this vector is dependent vector on the other two vectors. These two vectors are linearly independent. Okay, and how do we know this? By this result of this first theorem. Elementary row operations do not change null space or row space of a matrix. इसका मतलब क्या है कि जिस रो स्पेस को ये 3 वेक्टर्स जनरेट कर रहे हैं, उसी रो स्पेस को ये 2 वेक्टर्स जनरेट करेंगे. इस यहां से आपके पास जो स्पैनिंग सेट आया उसमें 3 वेक्टर्स थे. यहां से आपके पास जो स्पैनिंग सेट आया उसमें 2 वेक्टर्स हैं और दोनों क्या हैं? लीनियरली इंडिपेंडेंट है. व्हाट डज इट मीन? ये 2 वेक्टर्स जो हैं ये स्पैन भी कर रहे हैं रो स्पेस को और ये दोनों लीनियरली इंडिपेंडेंट भी है. व्हाट डज इट मीन? यही दोनों वेक्टर्स क्या होंगे? बेसिस भी होंगे रो स्पेस के. You got it? Any question? Any confusion? Anyone? Hamza?
All
Hamzala?
3 vector bases or just the 2?
Huh?
Sir, all 3 are the bases or just 2?
What did I just explain? अब बस इसकी भी कॉलम रो स्पेस होगी, इसकी भी होगी ना. रो स्पेस ऑफ A must be equal to what? Row space of B. क्यों? Due to this result. Elementary row operations do not change null space row space of a matrix. Means आपके पास एक मैट्रिक्स है, उस पे एलिमेंट्री रो ऑपरेशंस अप्लाई कर दें तो जो रिजल्टिंग मैट्रिक्स आएगा उससे जो रो स्पेस बनेगी और जो ओरिजिनल मैट्रिक्स होगा उससे जो रो स्पेस जिन वेक्टर्स जनरेट होगी, रो स्पेस दोनों की सेम होगी. अच्छा, इस रो स्पेस का स्पैनिंग सेट क्या है? स्पैनिंग सेट इसका क्या है? ए के रो वेक्टर्स. ठीक है, रो 1, रो 2 एंड रो 3 ये ए के वेक्टर्स होंगे. ठीक है, R1 from A, R2 from A and R3 from A. ये आप लिख लेंगे सुपरस्क्रिप्ट. इस स्पेस इस रो स्पेस ऑफ B को जो जनरेट करेगा वेक्टर सेट वो क्या होगा? रो 1 from B वेक्टर एंड रो 2 from B वेक्टर. क्यों? क्योंकि तीसरा वेक्टर तो 0 हो गया ना. दोनों 0 वेक्टर सिर्फ ये आपके पास. ठीक है, तो यही स्पेन करेंगे रो स्पेस ऑफ B. अब ये वाले तीनों वेक्टर्स जो जनरेट कर रहे हैं रो स्पेस ऑफ A को स्पेन कर रहे हैं, ये लीनियर इंडिपेंडेंट होंगे या नहीं? नहीं होंगे. क्यों? तीसरा वेक्टर इन दोनों वेक्टर्स का लीनियर कॉम्बिनेशन है. हमें कैसे पता चला? क्योंकि रिड्यूस एचेलॉन फॉर्म में ये वाला वेक्टर 0 होगा. What does this tell us? That this vector is a linear combination of these two vectors. Okay? It means this vector is dependent on these two vectors. So, जो रो स्पेस होगी B की उसमें ये 2 वेक्टर्स होंगे. अब ये दोनों वेक्टर्स जो हैं ये क्या होंगे? लीनियरली इंडिपेंडेंट होंगे. अगर ये रो स्पेस ऑफ B को जनरेट कर रहे हैं और ये लीनियरली इंडिपेंडेंट है तो रो स्पेस ऑफ B की जो बेसिस होगी वो ये होगी. और अगर रो स्पेस ऑफ B की बेसिस ये है तो रो स्पेस ऑफ B रो स्पेस ऑफ A के इक्वल है, तो रो स्पेस ऑफ A की भी बेसिस ये होगी. ये वाला सेट बेसिस नहीं देगा, ये वाला सेट बेसिस दे देगा डायरेक्टली. So if you want to find the basis of a row space of a matrix, what you do, you try to reduce that matrix into echelon or reduced echelon form, and then you check the non-zero rows in that matrix. Those non-zero rows, row vectors, will form the basis of a row space of B as well as the row space of A. It's easy, I think.
Sir, I had a question कि इसमें सबसेट की बात आती है कि ये R5 का सबसेट है, तो R5 का जो स्टैंडर्ड बेसिस सेट है वो भी इस रो स्पेस को जनरेट कर सकता है?
नहीं. देखिए, ये जो जो रो स्पेस होगी ये सब स्पेस होगी किसकी? R5 की। ये R5 की प्रॉपर सब स्पेस होगी, इम्प्रॉपर सब स्पेस नहीं हो सकती। दिस कैनॉट बी इक्वल टू R5 because R5 is a vector space which is being generated by 5 vectors. But here this row space is being generated by 2 vectors only. अब अगर R क्यूब में आपके पास 2 वेक्टर्स हों तो वो क्या जनरेट करते हैं?
सर प्लेन जनरेट करते हैं।
प्लेन जनरेट करते हैं, एंड प्लेन इज अ प्रॉपर सबस्पेस ऑफ R क्यूब. इट कैन नॉट बी इक्वल टू R क्यूब.
राइट, तो सबस्पेस होना जरूरी है।
डेफिनेटली सबस्पेस होगी. ठीक है?
यस सर.
You got it? Row space, column space अभी हम डिस्कस करेंगे. अभी हमने null space डिस्कस की है, and then row space of a matrix. अच्छा, इसमें एक दो थ्योरम और हैं जो मैंने आपको पहले ही बता दिए हैं. I'm gonna just read those theorems, you would understand. मैंने वो 2 theorems इसमें यूज कर लिए. What are those theorems? You can read those theorems, the statement of those theorems in my notes. They are very important in order to find row space and column space and null space as well. The second theorem, which I told you that elementary row operations do not change the row space of a matrix as well. This is the second. And the third one is a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. अगर इसमें आपके पास 2 equivalent matrices हैं, A के columns linearly independent कब होंगे? जब B के columns linearly independent हैं. अब जो इसमें तीसरा result है, a given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors of B forms a basis for the column space of B. ये वही बात है जो अभी हमने रो स्पेस के लिए कही है. हमने क्या कहा है कि ये रोज जो हैं ये रो स्पेस को जनरेट करेंगी अगर बी की ये रोज रो स्पेस को जनरेट करेंगे. ठीक है? अगर ये लीनियरली डिपेंडेंट है तो ये भी लीनियरली डिपेंडेंट होंगे. इसका मतलब क्या है? देखिए यहाँ पे सिर्फ ये 2 वेक्टर्स लीनियरली इंडिपेंडेंट होंगे. क्यों? क्योंकि यहाँ पे सिर्फ 2 वेक्टर्स आपके पास रिड्यूस एक्चुअल फॉर्म में 2 रो वेक्टर्स नॉन जीरो हैं जो कि लीनियरली इंडिपेंडेंट है. तो ये अगर लीनियर इंडिपेंडेंट है तो सिर्फ ये 2 लीनियरली इंडिपेंडेंट होंगे. ये तीसरे वाला लीनियरली इंडिपेंडेंट नहीं होगा क्योंकि इसके कॉरस्पॉन्डिंग रो जो है वो जीरो होगी. सो ट्राई टू रीड दीस रिजल्ट्स. Now there is another result which is a very important result which basically tells us the whole story. If a matrix R is in row echelon form, then the row vectors with the leading ones forms a basis of a row space of R, and the column vectors with the leading ones of the row vectors form the basis for the column space of R. What is this result? This theorem tells us the whole story. Means अगर आपके पास ये मैट्रिक्स है, इसकी रिड्यूस एचेलॉन फॉर्म ये है, तो वो रो वेक्टर्स जिसमें लीडिंग 1 आ रहे हैं, इसमें एक में लीडिंग 1 आ रहा है, ये लीडिंग 1 है. 2 वेक्टर्स हैं जिसमें लीडिंग 1 आ रहा है, तो यही 2 रो वेक्टर्स जो हैं ये बेसिस होंगी किसकी? इज अ बेसिस ऑफ रो स्पेस ऑफ A. Row vectors with the leading ones forms the basis of a row space, and the column vectors with the leading ones, कौन से column vectors हैं? एक ये है और एक ये है जिसमें leading 1 है. Column leading ones of the columns in the row vectors आपने देखना है. Leading ones जिस rows में है उसके vectors जो column vectors होंगे सिर्फ और सिर्फ वो लीनियरली इंडिपेंडेंट होंगे, बाकी सारे लीनियरली डिपेंडेंट होंगे. और यही कॉलम्स जो हैं ये बेसिस होंगी, बेसिस ऑफ कॉलम स्पेस ऑफ A. So this result made our life very easy. How to find the row space and column space and their basis of row space and column space. Okay. What is this result? ये result क्या है? ये हमें कह रहा है कि अगर आपने एक ही रो स्पेस और कॉलम स्पेस फाइंड करनी है, आप उसको रिड्यूस एचेलॉन फॉर्म में कन्वर्ट करें. अब रिड्यूस एचेलॉन फॉर्म में या एचेलॉन फॉर्म में जो वो वेक्टर्स बेसिस बनाएंगे रो स्पेस ऑफ एक ही, जिसमें लीडिंग वंस होंगे, पिवट एलिमेंट्स होंगे. सो दो वेक्टर्स में, दो रो वेक्टर्स में, दो रोज में पिवट एंट्रीज हैं. तो जिनमें पिवट एंट्रीज है वही रो वेक्टर्स क्या होंगी, बेसिस बनाएंगी रो स्पेस ऑफ एक ही. ठीक है. और कॉलम वेक्टर्स पिवट एलिमेंट जिसमें है, जिन कॉलम्स में है, वही कॉलम सिर्फ बेसिस बनाएंगे कॉलम स्पेस ऑफ एक. So if someone asks you to find the basis of a row space and the basis of column space and find the dimension of the basis of a row space and the dimension of the column space of A, what you have to do, you have to simply try to convert that matrix into echelon form. Echelon form में leading ones आपने देखना है किस किस रो में और किस किस कॉलम में. जिन रोज में लीडिंग वंस हैं वही रोज बेसिस बनाएंगी रो स्पेस ऑफ ए की, और जिन कॉलम्स में लीडिंग वंस हैं वो कॉलम्स जो हैं वो बेसिस बनाएंगे कॉलम स्पेस. आई होप यू गेट इट. इफ यू हैव एनी क्वेश्चन यू कैन आस्क. एनी क्वेश्चन? Now, what is the application of these things? Let me discuss the one last thing with respect to the linear system, and then the rest you can read in the book as well as in the notes. And we are going to finish this linear algebra thing, and in the next lecture we shall start differential equations. The basis for row space and columns will always be the same. Not same. They are not same. The number of elements in the basis set of row space and column space must be same. Means dimension of a row space and dimension of column space, they must be equal. Okay? Always dimension of column space of A must be equal to dimension of row space of A. Why is it so? Why is it so?
सर लीडिंग वंस जितने होंगे उन पे डिपेंड करता है ना.
मैट्रिक्स में हमेशा सेम ही होंगे, चाहे वो कॉलम्स में हो चाहे वो रोज में हो. ठीक है. तो लीडिंग वंस जो हैं वो हमेशा नंबर कॉलम्स में और रोज में सेम होते हैं. इसका मतलब है कि नंबर ऑफ एलिमेंट्स इन द बेसिस सेट ऑफ अ कॉलम स्पेस एंड द नंबर ऑफ एलिमेंट्स इन द बेसिस सेट ऑफ अ रो स्पेस, दे मस्ट बी इक्वल. अच्छा, एक और है रैंक ऑफ अ मैट्रिक्स. किसी भी मैट्रिक्स का रैंक क्या होता है? पहले हमने रैंक पढ़ा हुआ ना. रैंक क्या होता है? रैंक क्या होता है किसी भी मैट्रिक्स का? नहीं पता किसी को भी? रैंक बताया था यार, शुरू में हमने डिस्कस किया था. Rank of a matrix is the number of non-zero rows in its reduced echelon form. It is the rank of a matrix. हमने ये पहले पढ़ा हुआ. Rank of a matrix is what? Is the number of non-zero rows in the echelon form of a matrix. किसी भी मैट्रिक्स का रैंक क्या होता है? उस मैट्रिक्स को एचेलॉन फॉर्म में कन्वर्ट करें, उसमें जो नंबर ऑफ नॉन जीरो रोज हैं वो उसका रैंक होगा. ठीक है. अच्छा, रैंक को हम कैसे ले सकते हैं? एक और तरह से कि किसी भी मैट्रिक्स की जो एचेलॉन फॉर्म है, रिड्यूस एचेलॉन फॉर्म, उसमें जो नंबर ऑफ पिवट एलिमेंट्स हैं वो ही उसका रैंक होता है. ये भी कह सकते हैं. किसी भी मैट्रिक्स का रैंक उसकी जो रो स्पेस या कॉलम स्पेस की डायमेंशन होती है वही उसका रैंक भी होता है. हम इसको यूं भी ले सकते हैं. ठीक है? So rank is what? Rank of this matrix is what? Can you tell me what is the rank of this matrix?
2.
2. Okay? यहाँ पे rank of this given matrix A is what? It is 2, which is what? Number of pivot entries in the reduced echelon form of a matrix, or the number of non-zero entries in the echelon form of a matrix, or the number of dimension of a column space or the dimension of a row space of a matrix is called the rank of a matrix. And there is one more thing which is important here to tell you: nullity. What is the nullity of any matrix A?
The number of zero rows.
Yes, dimension of null space of A. Dimension of null space of A. It is called the nullity of the matrix A, and it is basically the number of, या आप इसको यूं कह सकते हैं, total number of rows minus rank of A. What is this n? It is the total number of rows. Total number of rows. या आप इसको कह सकते हैं number of zero rows in the echelon form of a matrix, or number of zero rows in the reduced echelon form of a matrix. या आप क्या कह सकते हैं? It's a dimension of null space of A. This is called the nullity of A. And there is a dimension theorem which tells us about rank, nullity, and the dimension of rank and nullity theorem bhi hai. Yeah, dimension theorem hai. I don't remember its exact name. Dimension theorem. ये देखिए, किसी भी मैट्रिक्स का रैंक प्लस उसकी नलिटी ये क्या आती है? इक्वल टू n, where n is what? Total number of rows. Rows of the matrix A. अगर स्केयर मैट्रिक्स है तो यहाँ पे रैंक प्लस नलिटी इज इक्वल टू द ऑर्डर ऑफ ए आ जाए. दिस इज कॉल्ड रैंक नलिटी थ्योरम और द फेमस डायमेंशन थ्योरम. यू कैन रीड दिस थ्योरम. अब यहाँ पे देखिए इसका रैंक क्या है इस मैट्रिक्स का? 2. नलिटी क्या है? 1. टोटल इक्वल टू 3. व्हाट इज 3? नंबर ऑफ रोज. नंबर ऑफ रोज 3. Rank, nullity. This equation should be satisfied. So it is satisfied. If you have any question, you can ask me. Otherwise, I'm going to stop it here. What is this? Hanzala Ahmed. Mathematicians love stating the obvious. But this obvious, it is very difficult to find it, even it is obvious.
Sir, I mean simple observation है कि non-zero rows पर zero rows total number of rows होंगी.
आप इसको किसी भी रो स्पेस की डायमेंशन, कॉलम स्पेस की डायमेंशन, नल स्पेस की डायमेंशन से रिलेट करें ना, then this result is very tough to prove. ठीक है? अगर आपको ये मैट्रिक्स नहीं गिवन, आपने इसका रैंक फाइंड करना है, इसकी नलिटी फाइंड करनी है और ये चीज प्रूफ करनी है. तो टेल मी हाउ वुड यू डू इट? ये मैथमेटिशियंस ने आपको आसान करके दिया यार. इसको रिड्यूसेशन फॉर्म में कन्वर्ट करो तो ये थ्योरम जो है वो ऑब्वियस हो जाता है. So any question? If not, I'm going to stop it. here today. I hope you have enjoyed today's lecture. See you next time, inshallah. Take care.